Well, thank you everybody for being here. Let's kick it off. So basically we're going to go, there's kind of like these two paradigms right now when it comes to being able to answer questions over our structured data. The text to SQL is something that I like to remind people that we've been doing for 3 decades or more, so this is not new. And I think what we're starting to see and kind of what we're pushing is understanding, is it really text to SQL or is it text to some semantics or the knowledge graph and then goes to SQL? So that's what we're gonna be talking about today. So in case you need to leave right now because there are other talks, to conclude, the conclusion of our work is that investing in knowledge graphs provide higher accuracy for LLM-powered question answering systems on structured data. And specifically, what we've been presenting is that the overall accuracy when you go work with knowledge graphs is 4 times more than if you don't include them over your SQL database. And which leads us really to the main, very bold statement that I'm making here is that if you really want to bring in AI, this new wave of generative AI and large language models to your enterprise, you need to go manage that knowledge, that context. And if you don't do that, you're going to fail. So don't be a failure. So that means that we need to start treating knowledge as a first-class citizen. And I think that's something that we have not been doing because we've been focusing so much on data, and I think we need to have that paradigm shift to focusing on knowledge. And I think now these large language models are giving us a motivation to do that. So the work that we're presenting here is a lot of work. I carry an academic background, and I think we need to have more industry academic collaboration. And I think this is the work that I'm presenting here is a result of industry and academic collaboration. So while talking about that, I carry 2 hats. I'm an academic by heart. I mean, I did my PhD. My work and my research has been on how to connect and integrate all these relational databases with what is now knowledge graphs, when it's all these semantic technologies, semantic web. So I've been working on this for almost close to 20 years. But I also carry my industry hat on, which I like to go work and make money and take all the research that we have done and actually put it out there in the enterprise. So I've always been this bridge between these kind of 2 communities. I've also written a book about designing and building enterprise knowledge graphs, and I also host a podcast, Cataloging Cocktails, the honest, no BS, non-salesy data podcast. We've been on it for almost 5 years now. So honest, no BS, life's too short for bullshit, so no drama. So I'm here to tell you how it is, how I'm seeing it, and I want you also to tell it back to me. So let's talk about knowledge graphs. I'm curious, so raise your hand if you're working with knowledge graphs. Very little, okay? Are you interested in it? That's why I assume everybody's here, okay. So this is the definition we have in our book, which is, it represents a collection of real-world concepts and relationships, right? And these are nodes and edges which form in the graph. And really the goal about knowledge graph is you want to be able to integrate data that's coming from so many different diverse sources, from unstructured to structured, all types of stuff. And from the word knowledge is really about the meaning. Like I really want to be able to go model things the way the users in that domain think about it. And the graph is just that very flexible kind of flexible data structure that enables me to take tabular data, put it into a graph, tree-like data, JSON, XMLs are tree-like data, do entity extraction, NLP type of stuff, and those usually come as triples into a graph. And I think like the knowledge graph is really kind of this modern manifestation of kind of this vision in computing that we want to be able to combine data and knowledge at scale. So actually, I really want people to go learn about this stuff. So hopefully you remember that link. Just take a picture of it. It's just going to go to Google, just request access, and I'll just send you the PDF of my book. I want you to go read this stuff. So take a picture, everybody. Get a free book. So when this whole knowledge graph, when we're talking about with LLMs and stuff, I wrote this article in the Communications with ACM a couple years ago. This really goes kind of through the history of knowledge graphs. And I think what's important for what I want people to realize is that we're seeing now this term more and more, but this isn't new. This builds on half a century of just computing advances that we've had on data and knowledge, again, for the last 50 years or so. So this is you can find this article. And then kind of, of course, we see ChatGPT coming out in November 2022. And then what happens very quickly, and we see this, is that people saying, oh, I want to be able to go chat with my data. I want to be able to go now have these conversations with my structured data. Because we've been doing all this text to SQL for so long, people are like, oh, I can just kind of pass things as prompting, whatever. So I remember we were actually at the Snowflake Summit, it was summer of 2023, and talking to the product folks at Snowflake, they were like, okay, we get that the semantics is needed and knowledge graphs and stuff, but show us, like, how does that work? And how well does it do? So we did all this research and we put out our work in November where we created a benchmark and we actually showed the first kind of set of results. It was actually 3 times more accurate around that. And then what we see after that, GraphRag kind of takes off. People have been paying attention to this, and this is people realizing, hey, these graphs, these knowledge graphs, when you look at RAG, right, retrieval augmented generation right now, especially on the unstructured world, it's like we hit these limitations because I'm just only looking at the similarity. I want to understand the relationships, right? That's the context. And people start realizing, yeah, graphs are important for that. And I'm like, I know, that's what we've been saying. So we continue doing our work, and there's another piece of work that we put out a couple months ago about how we can further use all these semantics, all these ontologies to really understand more and increase the accuracy. And actually, for this work, we got that to 4 times more accurate. And then what we start further seeing is like the GraphRag taking a lot of kind of heavier weight. The folks at Neo4j put out the GraphRag manifesto, and actually really cool to see that the reason why the number one reason that they said this is why graphs is because of the work that we've been putting out, the results. So let's start here. Over a year and a half ago, what was not well understood from a research perspective is to what extent these large language models can actually answer accurately enterprise questions over enterprise SQL databases. And I think in existing academic settings, again, remember, text to SQL has been going on for 30 plus years. Those existing benchmarks have been very academic and they have been very small scale. They represent the enterprise, and the questions that they're actually testing aren't very enterprisey. And then the other question is that we don't know to what extent knowledge graphs actually will improve that accuracy. That's what we think it is, but we don't know to what extent, how much is it. So the hypothesis we have is that if I take a relational database and I'm going to take an LLM and just answer the questions using just the stuff in the database, but then I have another version where I'm like, I'm actually going to invest and do all that knowledge work and create a knowledge graph representation over your database. And I ask questions in terms of the knowledge graph representation. Our hypothesis is that the accuracy is going to be higher for questions that are over the knowledge graph representation. That's our hypothesis, right? So I can falsify, I can create experiments around that. So if I were to draw a graph, that's what I would expect, meaning the y-axis is the accuracy. And really, I would like to have evidence to support this claim. Investing in knowledge graphs is going to provide higher accuracy for these LLM-powered question answering systems. So how do we get to this? Well, we first come up with a benchmark framework. Obviously, we have a database schema, and we actually wanted an enterprise SQL schema. So I've been familiar working in the insurance space. OMG is an object management group, an insurance standardization group, and they have an insurance property casualty data model. So we're using the enterprise schema for these things. The second, we want to have all these questions that we want to be able to analyze, and we look at them at a spectrum of complexity from the schema and the question complexity. And I'll go through these in detail. And then third, we want to be able to make explicit that context layer, that semantic layer. All that, and we're presenting these as the ontologies, the semantics, and the mappings, the transforms that connect these stuff together. I think existing benchmarks actually focus just on these first 2 parts here, and this part is not considered. So this is just a snapshot of a real-world enterprise data model for insurance, right? This is the property and casualty data model. So this is the messiness of the real world, right? So when we look at the questions, and what I want you all to take away, whoever's doing this type of work and thinking about it, is that if you're thinking about how to doing all this question answering stuff in your organization, look at it at these 2 different perspectives. One, we have this complexity of a schema, which is how many tables do I need to go answer a question? So low schema complexity, I need a couple of tables. High schema complexity, I need 5, 6, 7, 8 more tables. And then we look at the complexity of the questions, which is this an easy question or is this a harder question? And an easy question is one that's just give me a list of things, and a harder question is one that's about metrics and KPIs where you need some aggregation and some math. So for example, if I say a low question, low schema complexity is one that says, hey, just return me all the claims we have by claim number, open date, and close date. I just need to project 3 columns from one table. If I increase the accuracy over that, on the question complexity over that, I'm like, oh, I need the average time to settle a claim by policy number. So I need to join a couple more tables and do some aggregation, some math, some diff, but still a smaller amount of table. Now, if I increase the complexity of the schema, but it's still kind of an easier question, what I'm doing here is joining more tables, but I'm just still projecting some values. And at the end, when I have the higher ones, I'm like, I have to join a bunch of tables, and then I also need to do some aggregations and stuff. And these are the types of metrics, right? So total loss is a concept that every insurance company keeps track of. Loss ratio these are just kind of KPIs that are well-defined in the insurance industry. So for example, in the benchmark, what we do is that we provide these question-answer pairs. So given a particular database instance, if this is the database instance I have, and this is the question, this is the expected answer for it. So this is what we do for the benchmarks. So again, for organizations who are thinking about this and you're implementing these systems, look at this framework as a way of testing what you want to go do and what's working for you, what's not working for you. And it actually forces you to think about what are the questions that you do want to go focus on. And now increase the complexity of the question. You can see now I'm joining more tables and just doing some aggregate. So just kind of a quick highlight here of what this would look like underneath the hood. So for me to answer that question, I need to be able to join all these tables together. Now the context layer is actually the part that this is the point that we're making, is like I need to invest in this. If I invest in this, I'm going to have a higher accuracy for my question answering. So this is a visualization of the ontology of the semantics of what it means. You can see I talk about policies, and I talk about coverages, I talk about claims, and there's premiums and so forth. And this is using the terminology, the vocabulary of the business, of the domain users, right? It's not going down into the technical details this is your conceptual model, right? In your database, you have things that go down to your physical models. This is the conceptual model, right? The ontology semantics. And then what we also want is to make explicit these mappings, these transforms, right? I want to say, well, what is a claim? Okay, it happens to be that there is a table called claim, and everything in that table actually represents what the concept claim is. But if I want the claim number, I need to know that it's actually the company underscore claim underscore number. By the way, there's a claim ID column. That's not the claim number, right? So these are the mappings that we want to make very explicit. And then, but these mappings can get much more complex, right? So how do I know the relationship between a policy and a policy holder? I need to know that I need to join these particular tables together. I need to know that the code for policy holder is PH, right? You can probably guess why these LLMs, just with the SQL schemas, are not going to work, because how did they know that you had to use that column? It had to be PH and something else, right? So you have to do this type of work, and this should also be managed and governed. So this is the setup that we did for this benchmark. And again, I'm wearing my scientific hat on. So what I'm presenting to you is our basic, kind of the basic setup that we wanted to go do. We wanted to keep things super, super simple on purpose, because we want to take out any extra variables. So what we do is that we test like a zero-shot prompt for this. And the zero-shot prompt takes as input the question and also the SQL DDL, and I just pass that prompt to GPT-4, and we say, generate a SQL query for that. And then for the knowledge graph part, I'm going to go show you the bottom part first. What we do is that we create that after we've invested and created that ontology and the mappings, right, uses that context, we're going to use that to create the knowledge graph, right? How do we do that? That can be yesterday I gave a workshop on that, and actually you can read the book and you can see how to go build all this stuff. Now, in this case, in this setup, we have a virtualized knowledge graph, which means that my data continues to be stored in a relational database, in a SQL database, in Snowflake or whatever, and I virtualize it as a graph so I can write a graph query, in this case, a SPARQL RDF graph query, and then it gets rewritten into a SQL query over your database. I could have easily then used that I could have just materialized and had a physical graph database if I wanted to, but that's just kind of the setup that we had here. And this is literally the prompts we used. Super, super simple. Reproducible, right? This is science, we want people to reproduce this. Again, super basic. So let's talk about scoring. What do we mean by accurate? So we are actually taking the definition of accuracy from the existing SPIDER benchmark, which is the folks from Yale University who've been doing this for a while. So an execution accuracy means that it matches the result. It's a binary decision. You got it right or you got it wrong. And the orders of the columns and the labels of the columns are ignored. So that's fine. So if I say that if I have this question, return all the claims by claim number, open date and close date, and that's my expected answer, and let's say I generate a query that generates this particular result, this is an accurate execution. Even though the labels are different, the ordering of the columns are different, the rows may be different, it's still an accurate execution. Now, if I get this particular result, even though 2 of the columns were correct, right, that other one is not, so then the entire answer is inaccurate. So that's how we're defining execution accuracy. Second, we also want to we have to deal with the non-determinism of these LLMs. So if I ask, for this particular prompt, if I ask the prompt over and over again, not necessarily I'm going to get the exact same query back. So what we do is that we have this notion of an overall execution accuracy, which is I send the same prompt over and over again, and then I just test the result back and see how many execution accuracies that I got. So if I send the same prompt 10 times and I got back 8 of the times I got a query back that the result of the query was accurate, I got an 80% overall execution accuracy. Then finally, I want to bucket all these results, right? So I can do an average overall that. So either over everything or by those different quadrants that we presented. So when we do this, and we basically had almost like 40 something queries with that prompt, this is the result. I find this fascinating. I did invest some time and money and resources to go create that semantic layer, that ontology, these mappings, right? And you're all saying, you just raised your hand and you're like, you don't know, people are not working here with knowledge graphs. You may not know RDF and SPARQL. Look at this, how this worked. By the way, these standards, these are the semantic web standards, they've been around for 20 years. So these LLMs have been trained on the web. And again, I don't know, like a lot of it, why is this working so well? Well, a lot of it, I don't know what's happening inside these LLMs, but it's fascinating that by doing this investment here, I already got 3 times this improvement. Now, now we can look at this. This is the overall execution accuracy, and this is kind of a heat map approach, right? So the questions here at the bottom, if I ran it 100 times, I got it 100 times right. Things here are like 50%, kind of the 30%. Why did that happen? I don't know, but because we don't know what's happening inside these models. But what's most interesting is to look at what's happening by quadrant. So when we started sharing these results, I mean, it was kind of, people were already in their own testing realizing, oh yeah, if I'm going to just do pure SQL without any extra context, like the joins are going to really kind of, they're not going to figure out how to go do the joins. Well, if you're playing around with all these, I mean, everybody's now trying to go do this stuff, right? And you look at the snowflakes and the Databricks for genies and Cortex and all that stuff. What is their limitation? Only do things on one table. So, and that's it. I think they're just now starting to go push out things to go do joins and stuff, but because their focus is analytics, so it's only, really what you're doing is you're taking that dimension, that fact dimension tables, and that one table is that you're joining everything to one, and now they're like allowing you to not join it. But if I have different facts and stuff like that, they're so far off from that. So this is actually what people already realize, and that's why you see that right now, the limitation is that you can only do things on one table. But that's good. Now we know what's working. So again, here's the heat map result. So what would happen is that when we pushed this out in November originally, this actually kind of exploded. People really thinking about that, hey, we do want to, we really expect this future, and our executives are all asking, I want to be able to go chat, right? They're trying to play with ChatGPT themselves, I want to be able to go ask those questions over my data. And one thing is this unstructured world, but I'd argue that a lot of the most important kind of data that we use to go drive our results, to go drive our decisions, are coming from structured data, not from unstructured data. So they're all thinking about this stuff, and then what's really cool is that all these companies who've been talking about semantics for so long are like, hey, we finally have a reason to get people more excited about this. I mean, then we start seeing so many other companies taking the work that we have done and validating it. I mean, sometimes very well scientifically, sometimes just pure marketing, blah, blah, blah. But regardless, people are now paying attention to this stuff. And by the way, kind of from a scientific perspective, I find this fascinating because I remind people, and especially my students, is that science is a social process. The goal is I want to come up, I have an idea, I have a thought, I come up with an experiment, and I want to share the results, I want to convince my peers, and my peers are going to be skeptical, they're going to try those results themselves, and that's what we're seeing that's happening right now. So this is we're seeing science in action right now, super fast. Okay, so we now have a results of why things are working well, but what's really interesting for me is why aren't things not working? What can we learn from that? So if we look at the inaccuracies, if you're doing kind of with this approach, with this simple prompt and stuff, why did things fail for the SQL queries? It just, again, hallucination column names, hallucinated values. It would hallucinate all these joins I mean, the query would actually run, but it was the incorrect join to go do. But when we looked at the graph queries, and I'll show some examples here, the inaccuracy were the wrong paths. So if the path you had to get from A to B and B to C, the query that would be written would say A to C. So it was kind of getting it right, but it kind of missed the path, or it would get the wrong direction. You have to go from A to B, but it would write the query from B to C. So let's just show some examples. So this is a particular, the actual question, return all policies and their policy holder by ID. This is a SQL query, and this is a SPARQL graph query. And you may not know SPARQL, but I think if we look at this stuff, it's pretty kind of, basically we read it like a sentence. We say, if anything's a question mark, it's a variable. So this is a policy, basically. The policy has a policy holder, and the policy has a policy ID, right? So this obviously was the wrong value for party role code. It wasn't policy holder. And here it's actually didn't return the identifier for that policy. So it was the policy number. So it was close, this one, but I mean, it's still inaccurate. What is the total amount of premiums that a policy holder has paid by policy number? This column name doesn't exist. It created it. If we look at this question, it says a policy has a policy number. The policy has a policy holder. And then there's a coverage against that policy. Anyways, I asked for the policy holder, but if you look at the select clause, it didn't return it. So it was actually doing the right work. It just didn't return the policy holder, which I was asking for. So return all claims we have by claim number. Remember, claim number is not the claim identifier. It's actually the company claim number, that other column wouldn't know. That's correct here. What are all the premiums that have been paid by policyholders? I mean, this is all doesn't exist. This is a collusive value, and this is correct. So you see, a policy has a holder, the holder has an ID, a coverage has a policy, the coverage pays a premium, the premium has an amount, right? So almost every sentence is like in English here, right? So again, this is the hypothesis I have, that because the graph and triples is kind of like very English, so it works pretty well. I mean, what is the total loss of each claim by claim number, where total loss is the sum of the loss payment, blah, 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 blah. This is, by the way, this is the exact question that's sent to that prompt that I showed you. And I put in as just paste the SQL DDL. I paste that ontology in the turtle syntax, and that was the correct query. It's fascinating that this stuff gets it right. So to this point, I'm like, we have an answer actually. To what extent? Well, we know that it was up to 16% without any knowledge graph, and overall, it got that up 3 times more with the knowledge graph. So we see that this is now, we have an answer to that original question, right? So for me, that's evidence, strong evidence. for me to make this claim. But we got to keep going because I know what people will say is like, oh, I need 100% accuracy and so forth, right? I do want to caution something. It's like we all say we want to have the highest accuracy possible. What accuracy do you get today when you ask a question? Do you know? Do you ask a question and you get a report back in that dashboard and will you swear that that was 100%? Was the person who gave you that? So come on, calm down. Calm the fuck down. Actually, I think a lot of people, what was the joke I heard is like, you need to compare all these AI assistants like that first-year lawyer who has not slept in 4 days and who's reviewing your contract at 2 o'clock in the morning. That's the baseline that you got to compare to, right? So if I take, for example, here's a question. What is the total amount of premiums paid by policy number? In the insurance domain language, you have a policy, and you pay an amount for that policy. But really, what you have is that policy consists of a set of coverages, and then you pay amount for each coverage. But we usually have this language when we say it's like, oh, I paid for this per policy. So what you see is that the correct way for me to get from a premium is to get from a premium to the coverage and the policy. But a lot of these queries would go from a premium to a policy, for example. I'm like, but that's not the way. That's not the correct way. So these are the types of issues that we saw. It was an incorrect path. So this is where we actually thought, like, this is where semantics come in play even more to improve this accuracy. So let's take an example here. I say policy is sold by an agent. So what does this mean? It means that if I have that relationship sold by, that means everything where it comes from, the domain of sold by, is a policy, because policies sell something. And they're sold by an agent. So the range of this is always an agent. So if I were to ask a question, return all the policies that an agent sold. And this is the question, this is the query that I get back in terms of the knowledge graph. I say X is sold by Y, right? So this sold by matches with this, X matches with policy, and Y matches with agent. But what does that second line say? It says that X is an agent. But wait, if sold by, X must be a policy. Policies and agents are not the same thing. So what we could do is we can now look at the queries that are generated by an LLM. And because these semantics are defined and this is governed, right? We know who defined this and so forth. I can actually take those queries that were generated by an LLM and check them and saying, this does not match the meaning that we're managing. This is what I mean by the semantics. So we take this intuition and we're like, wait, can we do more of these checks in a deterministic manner, right? Now, no more LLMs. Like, we're now determining if we can actually further improve this. So our question now is, can we further increase, or how much can we further increase by doing these types of semantic checks over these queries? And then I was curious to know, like, what types of errors are these LLMs generating the most? Because I'm actually curious to know, like, can we try to understand what an LLM is doing? So again, the point is, if I do these semantic checks after the fact that the LLM generates a query, it would further increase the accuracy. So this was the previous setup that we had, and now we add two things to it. The first one is going to be what I call this ontology-based query checker, where we're going to take the query that was generated by the LLM, and then we are going to take also the ontology, that semantics that was defined. And we have a set of rules where we can check that deterministically. And if it passes all the rules, we say it's a correct query. And if it doesn't pass the rules, I now know that this is an incorrect, inaccurate query, but I also know why it's inaccurate. And we have a great friend who can do a lot of magical stuff, and that's called an LLM, and I literally will just say, hey, this query is incorrect for the following reasons. Can you generate a new query? It will generate a new query, and we'll try again. And we'll try this multiple times. And if it still doesn't pass after some kind of threshold or whatever, we just say, I'm not going to answer it. I don't know is a perfectly valid answer. So when we do this type of check, for this ontology-based query checker, we have a set of defined rules that we're firing. I'm going to just show one of them, where we're doing these checks. So let's talk about, this is a rule called the domain rule, which is the further example saying, if I have this property P sold by, then I know that the domain where it comes from must be X, and where it goes must be X. So in this case, if I have a query that says, AP, I'm like, wait, if it's P, I know it must be X, but you said it's A, so there I found that error. And this is just an example of how you can implement these rules. Actually, what's really interesting when you look at these knowledge graph technologies is that we can actually turn the query itself into a graph, and I can query the query. Right? So because you can turn anything into a graph in here. So this gives us a very powerful way of doing these types of, implementing these rules. And then how do we do this LLM repair? This is literally the prompt that we use for this experiment. You have this query with some issues, which are the following. Please rewrite it. That's it. Or just write and generate something. So when we do this, again, it's pretty straightforward and all reproducible. Like anybody can go off and reproduce this stuff. Look at that. Those questions that the accuracy at the first time was so low, we caught every time it was wrong. And after we would tell it to go fix it, and it jumped tremendously. And what was interesting too is that for even the easiest questions, we would catch the errors, and sometimes for a large portion we couldn't even figure it out, and we'd just say it's unknown. So then I can actually look at an error rate, which is the 100% minus the unknowns and the accuracy. This is the error rate. So even for the easier questions, the super easier questions, we're hitting a 90%, a 10% error rate. This is something now I can probably, 90% basically, it's like, this is something I can go compare to a user. And then this one, I want to dive more. I need to do more research on this. But what I find interesting, the domain and ranges. So domain is basically comes from the left side of that graph, and ranges from the right side. So most of the errors that it would find, were things that were coming from the domain, which means that was coming from the left side, which means basically that's how we write, right? That's how we read in English, left. So it's kind of like those. If an error would come up, it would come up from the beginning. So if we put this all together, right, all the results that we have, we're increasing, right? This increase of accuracy is happening because we are investing in these semantics. And I'll acknowledge that this work is being done by using these RDF knowledge graph technologies. People want to go test it out on something else, go test it out. My point is that it's investing in this semantics and this knowledge. It's what's making this improvement. By each quadrant to go do that. Right? So at the end of the day, what we have with our current approach, that's how we're getting that 4%, 4 times more accurate improvement. See, and then again, this is not a sales pitch around here, but as a scientist in our lab, what we're doing is that we are taking all these results and we're pushing them inside into our product. I think that's what I find fascinating. This is what I'm really excited about the role that I have. So we're building our own. We call it our context engine. And the way we view this is that there's 2 things. You want to be able to build that knowledge graph, and that knowledge graph comes from all your metadata that you're doing, right? So that's why I think a data catalog is going to be is a critical piece around that, because that's the place that you're going to be managing this. You're building that knowledge graph, and the other part is going to be your LLM. And what we're going to be seeing is that you're going to be building a series of different agents around this, agents. Wherever we'll talk about agents. And remember, agents is not a new thing. This is good old-fashioned AI. We've been doing planning and state machines for half a century. So agents is not a new thing. Please, I push people, go read a traditional AI textbook on this stuff. So we're building these agents that are going to be, that we want to be able to take the problem and break it down to smaller pieces and say, this agent, this program is solving this problem, and they're going to communicate with each other. That's why a lot of this stuff, we call this an engine, because you're really going to, this is not just a chat bot, right? The chat bot is going to consist of multiple different agents or different programs to go do this. So just kind of a high-level overview of how we're presenting this stuff in here is that I think today, when you look at the RAG architecture, right, you have a lot of these documents, they do all the embeddings and stuff, it goes into a vector database, and then you have all these applications. Your app is going to be, you're building some application, you're going to have that orchestration, things like LangChain and so forth, does your LLM, and then these applications get pushed, these applications does the RAG, right? It retrieves things from the vector database, and that's the whole RAG approach. What we're seeing, kind of the way we view the world, and this is our architecture, is that you want to be able to take sources like a Snowflake here. Yeah, we're Snowflake fans, we work a lot with them. So I want to be able to build and manage all that metadata, all that semantics, right? And I will be able to go call our metadata graph first, right? That's the basics of things. What are my tables, my columns, right? My business terms and so forth. And you're going to have all your governance, your data ops, your data catalog. This is just traditional vanilla data cataloging governance. But then you also want to start building is that business graph, right? And that business graph can be materialized, can be virtualized, but that's where this business graph, I'm actually talking about the concepts of policy, coverages, premiums, customers, products, orders, and so forth. I'm talking about this here, and I can now query the data in terms of products, customers, orders, right? And then you'll have these agents that you're building, and these agents will be about answering a question. These agents will be about interpreting a question. These agents will be about explaining the answer of the question I want to. So actually our internal system based on this benchmark, and by the way, I'm talking about our benchmark here, but I also want everybody to acknowledge, please take any results from a benchmark with a gigantic grain of salt, right? Something like these stuff changes all the time. This is an indicator for this particular scenario, but we should not generalize. This is the results for this particular benchmark. So with our internal system, which we've done, which we included these 3 techniques that I've presented here, overall we are at 93% of our current benchmark. And then if you actually look at all the different quadrants, yeah, we're hitting over the 90% per this particular benchmark. So the takeaway I want you to all have is that if you truly want to be able to have this chat with your data over your structured relational databases, this is going to work if you make an investment in that semantics, in that knowledge. And I've shown you, if you implement that in a knowledge graph, how it's already working. There's obviously so many challenges. And this is just a quick laundry list of challenges that we're encountering right now. How to deal with these ambiguous questions, right? So people are going to start writing, what are my best sales? What does best sales mean, right? How do I keep track of that? Should I govern and have a business term for best sales? Or should I have a process where I'm going to work with the user to disambiguate what you mean by best sales, right? These are different approaches that we're all taking into account. Unanswerable questions. I ask a question and I know that this is something that we don't have any knowledge about, and I should be able to say, I'm not going to answer it because we have nothing about it, instead of trying to go figure out what an answer could be. How do we deal with default assumptions? So if you're asking a question, for example, what is the top countries by GDP, the top 10 countries by GDP? If I ask that question. Yeah, so you're expecting all the countries, right, with a number. But what happens if I return to you Monaco, 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 Monaco? Well, there is an assumption that there's always a year. So what is that year when people are asking these things, right? So that's something that we need to consider. What do we do with default assumptions? What happens if I have multiple aggregations or multiple questions in one? The one that I talk about now, it's interesting, is strings versus things, right? What if I'm talking about a product? I have fluffy slippers, right? But how are people writing that? How am I matching that? So how am I dealing with the strings versus things? Dates is always an interesting stuff. There are a lot of interesting challenges. So to wrap up here, my call to action with everybody is that when it comes to this AI and these LLM world, there is the notion of trust. How do we trust these systems? And for me, the way I'm defining trust is three things. One, we have to deal with these hallucinations, right? These LLMs, these models don't know the facts of the organization. So how are we dealing with accuracy? So trust is about accuracy. We have this black box nature, right? Something is happening and I get an answer back. What actually happened? Explain to me. I mean, if you tell the LLM, give me an explanation, the explanation itself could possibly be hallucinated. So explainability is going to be part of trust. And finally, there's all these issues about risk, is it being exposed and so forth, the data is being exposed, how's it being used, so we need to have governance. So for me, my definition of when we need to provide trust for all of these AI systems, we need to make sure it's accurate, we need to make sure it's explainable, make sure it's governed. And everything I presented to you up to now, it's just on accuracy. So we're really obsessed right now on accuracy. We also need to think about on the explainability to whom, and part of that is the governance. So again, call to action is like, yes, accuracy, but there's other aspects. And in my lab, we're working a lot on explainability right now. So more call to actions of folks. From a technology perspective, I said, if we invest in knowledge graphs, right, we invest in semantics and knowledge, we're going to increase the accuracy. Okay, but I need to make this investment in knowledge and semantics. So what are the ways that we can reduce that cost itself, right? So again, we're also in our lab working a lot on how to do all this knowledge engineering co-pilots to be able to go do this. Yeah, how do we best create and manage these contexts? My position is that this context should live in an independent layer. I'm biased here, but I think it should be in a data catalog and a metadata management system. Second, what are the processes? What are the methodologies to go follow around this? How do we do testing today for these new LLM systems, which are non-deterministic, right? We're entering a new era of testing like how do we create internal benchmarks that we can go do? Third, I think there's the people aspect, which is I've been advocating for a long time. I've called this the knowledge scientist, and you can go to knowledgescientist.org. It's also knowledge engineering. We've been doing this in the 90s. This is about the people and the knowledge side, and how do we able to capture and manage that? I think we need to start thinking more about this type of role, which we're already doing today, but that's where we need to go. So we start off with this, and you know where I'm placing my bet. If I want to be able to do all of this, answering questions over our relational SQL databases, I'm betting on knowledge graphs because I bet the other one is the loser. So to conclude, investing in knowledge graph provides higher accuracy for LLM-powered question answering systems over your structured data. Our scientific evidence has shown that it's over 4 times more accurate around that, which means, hey, if you want to be successful, invest in knowledge graphs, invest in semantics and knowledge. If you don't, you're going to fail. That means we need to start treating knowledge as a first-class citizen. And with that, thank you very much.